Okay, there we go. Here's where we were last time. We were talking about how to deal with the fact that sometimes we want to make an accumulation argument, chop it up, add it up, the whole sum of the parts. But the dimensions don't line up. And so if I were to, for example, ask, how would I do an integral on this domain? Well, the domain itself, if you look at the actual domain, it's one-dimensional. But I can't really do a Calc 1 single variable integral on it because it's not on the x-axis or t-axis or something, right? But then maybe it's a double integral because it lives in a two-dimensional space, but there's no area involved here, right? So this is just a weird situation. It does not fit with any of our pre-existing constructions, so we make some new constructions, right? This is where we ended last time. We just made a new kind of Riemann sum that's just tailor-made for exactly what is going on in this scenario here. Namely, we've got little pieces of curve. Curves have length, right? So we can talk about how big that little piece is by talking about its length. And then stuff is distributed in the sense of mass per unit length or stuff per unit length, whatever the nature of the stuff is, etc. So we therefore came up with this new concept of a line integral. That terminology is historical. Line is a regrettable choice because it's a curve. It's not necessarily a straight line, but this was, I guess at the time, the term line was understood to just mean anything that you can do with a pencil, right? Curves included. And then likewise here, a surface integral. Now, for reasons that won't be clear just yet, we're going to modify those terms. This is not just a line integral. This is, we have to be more precise, this is something called a scalar line integral. There is a different kind of line integral that we're going to see very soon, probably next time. But I'm going to leave the details out for now, just for dramatic purposes, let's say. And then likewise, this is a scalar surface integral. There will be a different kind of surface integral that we'll see later. Okay. All right. So now how are we going to compute these things? And I say broad stroke, we've already actually seen the method, kind of, at least strategically. And that is, we have a domain that we don't like. This surface here, for example, let's see here. There we go. This surface is a bad domain. We've seen bad domains before, domains that we don't like because they have corners and awkward places, or because the edge curves are uncomfortable algebraically, something to that effect. And so what do we do in that case? We do a change of variables. More precisely, we view this undesirable domain as being an image, and then we do a pullback through that function whose image is this undesirable domain, accounting for, of course, how stretching factors will play in, right? And then the result is that we end up with a new integral over a nicer domain, presumably, hopefully, fingers crossed, and then we can do the integral on that nicer domain. So this big picture strategy, we've already seen it with change of variables, and we're just going to have to adapt it to this new circumstance. Okay, so let's start with a curve. If you have a curve like so, this is our domain. We don't like this domain. It's dimensionally weird. I don't know how to deal with that, right? I mean, directly. So we're going to view it as being an image. I'm going to view that curve as being the image of some function defined on a different domain that I like better, and I like this interval over here better because it's dimensionally natural. It's a one-dimensional interval that lives in a one-dimensional world. So how do we do this? How can I view a curve as being an image of an interval? Good news, we've already done that. That's called a parametric curve. Right? Been there. We already have this construction. So short version, all we need to do, if you have a domain that you don't like because it's, a curve in the plane or a curve in space, whatever, just parameterize it. Figure out some way to parameterize it in various different methods, of course. And then when you pull back through that parameterization, details to follow. But when you pull back through the parameterization, your new domain will be this interval over here. Okay. All right, so let's talk details. We know that there's going to be, to some extent, just plugging in. That part we can handle. The big mystery always is, what's the stretching factor? By what factor is this length different from that length? Right? And parameterizations are going to effectively take our interval and drop it into the plane, but having been bent and contorted and possibly stretched, among other things. So we just need to know by what is this factor, what is this factor by which the orange length is stretched out to become the green length. And so we're just going to compute this green length here. And I'm going to, just for artistic purposes, easier to visualize, remind you that with this bigger picture, that with that little piece of curve we can look at, and don't forget from a while ago we defined this thing called the dx vector. Over the amount of time that it took us to cover that little green length of curve, of course, the actual change in position, I missed. The actual change in position is that blue vector. But it was hard to see that coming as of this particular moment where we only know the velocity and how much time it's going to take. And so we have to look instead at this differential. Not the actual position increment, but the position differential, dx, right? This is our linear estimate, because this is something we can get our hands on. And we can get our hands on the dx vector pretty easily. In fact, let me just kind of cut to the punchline here. This dx vector is velocity times time. That's old news, right? We already knew that. So why am I wasting all this time up here with all of this stuff? And this is just to set up a pattern that we're going to be taking advantage of on the next page. Just for pattern purposes, let me go through this. The idea is our dx vector has various parts, and one part of it is, well, how much did the x coordinate change as I, moved along this piece of curve? And how much the x-coordinate changes is a statement about derivatives. Okay, straight up, single variable calculus, no big deal there. And then likewise, how much did the y-coordinate change? Again, single variable calculus, no big deal. I can just look at output change, input change, derivative. Is everybody happy with that? Okay. So, then the observation I make here is just that the actual vector differential is just made up of, well, of course, the differentials of the individual coordinates. So that's all, no big deal, right? And anyway, you can take this formula for the position differential. Note that the length that I'm interested in here, ds, is the magnitude of that. Right, again, flashback to early chapter 13, I think it was. Then we're going to take this formula for dx, plug it into there, play through a bunch of details. Too far. And here's the formula for what ds is. And very importantly, though, now I'm going to get rid of all the clutter. Very importantly, if you look at how this formula ends up, let's see here, let me go back to here we go. This output size, ds, is being related to this input size, dt. And you can see right here in this formula what the stretching factor is. By what factor is ds different from dt? And there it is. It's the speed. It's the magnitude of the velocity vector. So, again, I could have gotten to this conclusion immediately by saying distance equals rate times time, right? Of course, right? But again, the method is going to be relevant to what we're going to do on the next page. Okay, so we've got ourselves a stretching factor, and now that we have a stretching factor, well, we can just start writing down how to compute these scalar line integrals, because here's a scalar line integral. This is a chop it up, add it up argument on some quantity that accumulates over some curve, and I can just rewrite it like this, because after all, I've got my stretching factor. Namely, I've got my factor that tells me how much ds is compared to dt. And everything else is just plugging in and pulling back. Okay, and of course we like this because this is a single variable integral and I totally know how to compute it. Examples to follow. But before we do that, I want to do the same thing now for surfaces, because it's a really analogous argument. But this really analogous argument here is going to be in a situation where I can't just refer back to some old high school physics formula like distance equals rate times time. I'm going to need the coordinate point of view on this that we set up on the previous page. So here goes. Surface I don't like. It's dimensionally weird. Two-dimensional thing, three-dimensional world. It's not a double integral. It's not a triple integral. This is a problem, right? So how do we compute this? Well, among other things, we're going to parameterize the surface. We'll talk about how to do that in a few minutes. But for the moment, I just want to assume that I've got a formula given to me. Let me do this in purple for consistency. I have a formula here that allows me to take a point u comma v, and out will come a point on the surface x comma y comma z. Right? And again, we'll see some examples, and I'll show you how to create these, etc. But if I have this, then, having parameterized the surface, again, I'm just going to pull back. When I do the pull back, my new domain here is a two-dimensional thing in a two-dimensional world, which is fantastic. We already know how to deal with those. And all I really need is a stretching factor. So again, I need to understand how much area that is, but more to the point, I need to know how that is a multiple of that area right there. So again, I need to know how much does the parameterization stretch out areas. By what factor is green different from blue? Is everybody with me? Yeah. Okay, so here we go. We're going to look at that green piece of surface area. And let's see here, my picture, oh gosh. It's a hard piece of art to deal with here. Here's a little piece of surface. And just like with a piece of curve, it's not flat exactly, but it's almost flat. It's close. And it's well approximated by what I'm going to call these edge vectors. Oh, man. Try to get these. It's harder than it looks. This edge vector and that edge vector, which between the two of them will create this parallelogram like so. And what I'm actually interested in, of course, is this green area, but you know what? It's really well approximated by this yellow area, and that yellow area is something I can get my hands on. It's a parallelogram in space. We've got formulas for how to compute the area of a parallelogram, right? It's like, what is it, magnitude of the cross product, right? The old fact from chapter 12. And Math2, excuse me, I wires crossed for a second. Back from chapter 12. Yeah. Okay, so, how do I compute that area? Well, I need to understand this purple vector and this blue vector, and I'm going to take these one at a time. just to keep things simple, let's think about this purple vector here. And the first thing I'm going to argue is that purple vector is the image of this red vector over here, let's say. And in particular, this is what you get when you move along one edge of a little square, one side of the blue area that we're going to eventually try to relate this to. And what happens as I move along this red line? Well, there's two things I can say about it. For one thing, as I move along that red line, I am moving in the u direction. And so any derivatives I'm going to be talking about will be derivatives, partial derivatives with respect to u, because v is constant. Everybody on board? So in fact, all of these derivatives that I've got down here are all going to be partials with respect to u, because u is the only input variable changing. And then the second thing that I can say is, let's see here, color choices. Let's do this. How much is u changing? Well, u is changing by whatever that side of that little rectangle is, and typically we call that du. So I'm going to be multiplying a u partial times du. That's just what my input setup says. And with that established, then now it's a matter of kind of looking at one coordinate at a time. If you want to know how much the x coordinate changes as you move along the u direction by an amount d, if you want to know how much x changes, there you go. We're just keeping track of how x changes as I move in the u direction and by an amount du. And if you want to know how much y changes, boom. If you want to know how much, color choices, I'll use yellow. How much does z change? Well, then same thing applied to z. So this vector here, this purple vector that we need to get our hands on, I see its coordinates. I can just write down its coordinates. There they are. And then I can notice all those coordinates have a common factor of du. You factor them right out, and bam, there's our formula for this vector here. How we doing? Everybody follow? Okay. All right. So getting rid of my mess here. Easy formula for that vector, as it turns out. Now, analogously. That's fine. Analogously, this vector, that's what I get when I'm moving like so, namely in the v direction by an amount dv. And so you make the analogous argument, and the nice punchline is that vector is this formula right here. So good exercise. Think that through. Make sure you're comfortable. It's all over but the shouting. We've got these edge vectors. These edge vectors, all I have to do is figure out now what the area of the corresponding parallelogram is. And again, chapter 12 formula. The area of a parallelogram is the magnitude of the cross product. So magnitude of the cross product of these edge vectors that I just got through motivating. And then I notice, how convenient is this? I can actually see some scalar factors in here. This scalar du, I can factor right out. And this scalar factor dv, I can factor right out. And so now here's my updated formula for the output area. And conveniently, lucky break, what I am seeing is this output area being written furthermore as a multiple of the input area. Let me just remind you, right? So the input area is the area of this rectangle. That's du times dv, right? Input area. The ds that we just computed is this output area. And so what is it that you multiply by input area to get output area? Here then is our stretching factor. That's the thing that allows us to do the pullback. That's the one little ingredient that isn't sort of just a matter of kind of plugging things in, right? And that makes our integral turn out as follows. So again, if you have a ds, I can pull back that ds and write it in terms of du and dv with my stretching factor that I just computed. Everything else is plugging in. Everybody on board? Okay, so as it turns out, this stretching factor, the magnitude of a certain vector, this certain vector, you'll notice, is a cross product. It's xu cross xv. It turns out that this vector is important for various reasons. It's not just a vector whose magnitude happens to be the stretching factor in that parameterization. For example, you're going to notice also it's always perpendicular to the parametric surface. You can actually see that right here in this picture. After all, xu points that way and xv points that way, both of those being tangent to the surface. So that cross product being perpendicular to xu, being perpendicular to xv, is also perpendicular to the surface itself. So neat fact, right? And that's going to end up being really useful later on, but not particularly right this second. But that will be a useful fact later on. Anyway, punchline. This vector is worthy of having a name and a notation. And so we're going to call this the parameterized normal vector. And use this notation, capital N, which seems to me to be standard. I've seen this in multiple books, and that's fine. Reasonable choice. Okay. All right. So then, with that notation in mind, our stretching factor, I can rewrite, right, because that's what N is. So stretching factor is now just the magnitude of capital N. Notational little convenience, I think is handy. The book agrees. Okay, so now a real quick aside. I've computed a stretching factor in a situation that was analogous to change of variables, and I'm going to suggest it'd be a nice little bit of mathematical weightlifting. If you want to know, how well do you really understand what I did here? Do an analogous argument and derive the stretching factor for change of variables. And just to get you started, let me just point out the very, very strong similarities here. Here I was looking at a piece of surface, and so it was implicit in this picture. Whoops, I wanted this to be in pencil mode. Sorry, it was implicit in this picture that we were in 3 dimensions. That was the whole awkwardness in the first place, that we had a 3-dimensional output but a 2-dimensional input, and that's why we had to kind of deal, right? But the difference in 2 dimensions, if this was a 2-dimensional change of variables thing, it's just that, now there's only 2 coordinates. And so all of this stuff, this part of the picture just kind of disappears, and now we're looking just at something in 2 dimensions only, and there's going to be, here's a little piece of area that we want to understand. It's just that now that's an area in the plane. It's not floating in space. And there's these edge vectors there and there, and I've just got to figure out their coordinates. Now there's only 2 coordinates now because we're in the plane. And then I've got to figure out how to compute the area of this parallelogram, but now this is a parallelogram in the plane, not in space. How do we find the area of a parallelogram in the plane? Well, it's a different little Chapter 12 formula that we established at the beginning of this course. So But the details really will look a lot like this here. It's just that there's only the two of them. There is no third coordinate. And then, again, different formula for how to compute area. And what you're going to find, if you go through the analogous calculation, you're going to find that you derive the stretching factor for change of variables, being the absolute value of the Jacobian determinant. So it's a good exercise. I hope everybody will give that a shot. If you get stuck, come to office hours. I'll be very happy to walk you through it. It's a good bit of mathematical weightlifting. Okay. All right. Let's do one. We have here a surface pre-parametrized for us. Again, this is a get started example. We'll talk later about what to do if your surface does not come pre-parametrized. Right? But here it is, already parameterized. And notice I've got three outputs, x, y, z, and they seem to be functions of only two inputs, u and v. That is a parameterization of some surface. Surface. And then I've got a density of mass distributed across that surface. So non-constant density. Notice that the density depends on location. Different places on the surface, different x, y, z, you're going to have different densities. And how would you compute, the question asks, the total mass? Okay, so, alright, we're going to make a chop it up, add it up argument. The mass that we're interested in, the whole is the sum of the parts, and on each little part, it's mass per unit area times area. Everybody good with that part? We've just got to figure out now, how do I compute this scalar surface integral that we just defined? And of course, we're just going to use the formula on the previous page. Here you go. If you want to compute a scalar surface integral, then apparently we're going to need to know this thing called n, which is the cross product of these partials. So I'm going to have to take partials of my parameterization. My parameterization, normally I would have to figure out how to create that as well. But again, here, lucky break, pre-parameterized surface, and so I have my parameterization given. So, take the partials per the formula. We take the cross product of those partials. Now, I'm leaving out those details, right? Y'all know how to do partial derivatives. Y'all know how to do cross products. So just make sure that you, and again, always a healthy exercise whenever I, sweep some details under the rug like that. Make sure you follow through, double check me. Think of it as you don't trust me to get my algebra right, which by the way, is also probably healthy, right? But think through those details and make sure that I got it right, or said differently, make sure that you can get it right. Okay. And then, again, to get the stretching factor, we plug in to this formula that the stretching factor is the magnitude of that capital N vector, and out comes our stretching factor right there. And now we're in business. And now we can do the pullback. It's all plug and chug. Everybody okay so far? Let's just be thorough. Let's actually do the plugging and chugging here. Let's see. We've got already an argument about this being this scalar surface integral. Check it out. I have a formula for density. Oh, let's see here. Color choices. Density is given. Now, wait a second. Where did all that U and V funny business come from in here? Well, it came from the parameterization. Now, I will remind you, just like with change of variables, when you pull back, aka plug in, those details are in the parameterization. And so, for example, this x right here, there it is. That's where that u plus v comes from. That's x. So says the parameterization. Right? Y, well, again, it's right there. There's a formula given to us. So that's where that comes from. And then what do we do with this z? Well, z is 2v. So the parameterization tells us how to do that plugging in. Is everybody cool? Okay. Then there's the question of the DS. Of course, DS is just stretching factor times du dv, and we've already computed our stretching factor to root 14. So, boom, we're in business. Everybody happy? Okay. Very pluggy-chuggy. Oh, one little detail I left out. Now, of course, when you do a pullback, right, you need to know what your new domain is. The domain is literally going to be just the values of u and v, whose image gives you the surface itself. Namely, your pullback domain is just going to be whatever part of your parameterization tells you where that parameterization is defined. And in the statement of the question here, it actually tells us right here that these are the values of u and v that when you plug into the parameterization gives you our surface. And so those then are the values of u and v in this integral. What do you say? Everybody's happy? Okay. All right. Okay, so now let's address the elephant in the room. How often is it that when I encounter a problem like this, that the parameterization is going to just be handed to me on a silver platter? Probably not in the real world. Anyway, possibly, but probably not. So how do we parameterize surfaces? And there are various different versions of this depending on the circumstance, but I'm going to show you here my favorite one. This is the one that works most often. This is definitely, if I had to pick a single method for parameterizing surfaces, and I can use this and this only, my desert island surface parameterization technique. This is it right here. It's what I like to call the graph parameterization. So the big idea here is a surface. This surface, however, is currently written as an equation. You might say it's written as a level set. What we need to do is to figure out how to write it as a graph. Thus the name graph parameterization. So how do we make it a graph? Well, we solve for z. A little bit of arithmetic, algebra there. Easy algebra. Now that it's a graph, here's the big trick. Really powerful trick. Whatever variables are the inputs, we're viewing, you'll notice here, z as being a function of x and y. Whatever variables are the inputs, let those be the parameters. That's the big trick. Once you've got it written as a graph, once one variable is a function of the other two, those other two, let those be your parameters. Let's say u and v, or s and t, or whatever variables you prefer. I claim it's all over at this point. In fact, we actually have a parameterization. We just haven't kind of quite, run it into the end zone quite yet. But look, if x is u and y is v, then I've already got formulas for x and y in terms of u and v. They are u and v. And with that noted, I don't actually have any choice anymore as to what z is going to be, because if x is u and y is v, those you have to plug in there, and the punchline is that z has to be that. And so this is, right here then, the parameterization that just comes immediately out of these choices. Everybody on board so far? So two-step process. Step one, solve for one of the variables in terms of the others. In other words, write it as a graph. Step two, let the input variables be your parameters. And I guess let's call it step three, write down the resulting parameterization that is already determined. Everybody happy? Okay, so here's an example. Let's suppose that for whatever reason I'm interested in this surface right here, the upper half of the unit hemisphere. yeah, maybe I want to compute the amount of mass on there, or maybe, whatever. Maybe there's ants crawling around all over it and I want to count the ants, whatever. Okay, so, that's going to be a surface integral, whatever it is I'm interested in. I'm going to need a parameterization. Let's invoke the graph parameterization here. Let's use the method that we just identified. And notice that in this algebra right here, I can solve for z. Very importantly, because it says right here z has to be positive. And so when I look at that z squared and I take a square root and I get worried, how do I know which is it going to be the plus or the minus? I don't have to worry. It says right here z is positive, non-negative anyway, so I don't have to worry about the minus. Okay, so solving for z gives me that formula. Now I've got it written as a graph. So that was our step 1. Step 2, let the input variables, you'll notice are x and y in this case. Let the input variables be my parameters. So here I have x and y being u and v. And then it's all over but the shouting. Z has to be that. And I've got myself a parameterization. So this x, y, and z is functions of u and v, parameterizes my upper unit hemisphere. Is that cool? Okay. All right, now let's talk about the domain for this. And this is a tricky part. A lot of students get confused on this. When I do a pullback here, right? What's the range of values of u and v? And so imagine, in other words, that we think about, we've got this parameterization function that does like this, and I've got my pullback domain is in the uv plane, and my target up here is in xyz space. But what is this pullback domain? And I've got it drawn here as a disk. Why is it a disk? Because the range of values of u and v is exactly the same as the range of values of x and y, because u and v are x and y, right? This is the big trick, right? So if you want to know what u and v are doing, ask yourself, what are x and y doing? And on this picture, you can just straight up see that over this entire hemisphere, the x and y coordinates are always going to kind of put you on that little disk right there. And so u and v, likewise, are on that disk. And let's see, was this a unit disk? Yeah, that's right. So unit disk, because the radius there is 1. Now let's take a pause on this. I'm going to make sure everybody's comfortable with what happened. Yeah, question?
Initial surface, is it like a 2-dimensional, just like a half circle?
Yeah, well, it's the original surface up here is the hemisphere. So it's this surface up here.
Okay, it's just that surface and then in 3 dimensions. Right?
That's right. It lives in 3 dimensions. That's right. It's a weird thing. It is itself intrinsically 2-dimensional because it's a surface, right? But it lives in a 3-dimensional world. Yeah. Cool. Which again is, why people were confused about the shape of the Earth, right? Because it really feels 2-dimensional as we walk around myopically, right? Only able to see, teensy tiny little distances away from where we are. You can't see the curvature. So it feels 2-dimensional. It is locally 2-dimensional, but it lives in a 3-dimensional world. Yeah. All right. Cool. Now, here's an alternative. Basically the same idea, a little different, and that is to think about a different coordinate system. So that surface that I was just looking at, I had previously written it in rectangular coordinates. Here's the equation in spherical coordinates, rho equals 1, right? It's a unit sphere, so it's easy to write down. And again, check it out, I have solved for one of the variables. It's just that now I didn't solve for a rectangular variable. Now I've solved for a spherical variable. Can I use this? Can I do a spherical graph parameterization? This, after all, I'm viewing it right here as a spherical graph. Can I make a spherical graph parameterization from it? And the answer is yeah, absolutely, no problem. The only little twist is you do have to start with the conversion formulas for x, y, and z. After all, x, y, and z are always these in terms of the spherical coordinates, and then just plug in your spherical variable that you've solved for. It'll usually be rho, right? So I just plug that in there, and there, and lo and behold, as we hoped, we have position. Okay, let's try that again. Position as functions of two variables. Now this time they're called phi and theta instead of u and v. Whatever. It's still 2 inputs, 3 outputs. And this is a parameterization. Everybody on board? Okay, now you do again have to think about the range of values of these variables. And in this case, you got to think a little bit differently. Looking at our actual surface here, again, what is happening to what is happening to phi and theta on this surface? Well, I think it's a pretty easy pitch that theta goes all the way around. So theta goes from 0 to 2 pi. All right, there you go. Theta goes from 0 to 2 pi. There's our theta axis. And then what's phi doing? Conveniently, phi, no matter what theta is, phi is always going from 0 to pi over 2. That's just what our actual surface is doing. And so, okay, fine. So phi, 0 to pi over 2. And so the pullback domain is this right here. It's this rectangle. And again, we had to kind of reverse engineer this from the geometry of the given, but nevertheless, it's just again a matter of looking at the range of values over the original, the variables in question over the original surface. Yeah.
How would you, for a rectangular one, how would you compute the stretching factor? Would it be on Z?
Oh, no, the stretching factor formula is all the same. Once you have a parameterization, where you got the parameterization from kind of doesn't matter. I have here x, y, and z as functions of u and v, and the stretching factor is that formula. Always the same, right? It's always you got to take the partials, take the cross product, take the magnitude. So apply. We're going to do that in just a second. We're going to do it in just a second, right? But same formula. Now you'll notice I have here 2 different parameterizations, right? So I've got 2 different parameterizations of my same surface. We got to decide which one we like better, I suppose. But in both cases, take the partials, take the cross product, take the magnitude. Is that everybody happy? Okay. Now let's speculate. I think this is a fun little exercise. Which one of these do we think is going to be better? And I got to tell you, my money would have always been on this one because okay, fine. There is the one little square root here, and I know that I don't like square roots, but look at all of the trig in that one. It seems like this is going to turn into a trig nightmare. Potential. Y'all can probably tell how this is going to turn out. So here's the algebra, and it's just a matter of noticing that when you take that one little innocent-looking little square root, it was just the one, right? But that makes square roots show up, and now in the denominator, that's even worse when I take the partials. Then when I take the cross product, still not great. And then when I take the magnitude, I end up with this, and let the record show I just swept a bunch of algebra under the rug as well, right? But my stretching factor here has a square root in the denominator, and thus an innocent little calculation, for example, of just area. A calculation where my integrand itself is just 1. right? Because of that stretching factor thing, that area turns into this. My stretching factor is all of that, and my resulting, what do I actually have to punch up? It's an ugly integral. And it's doable. Right? I mean, but it's weird. This is not a fun integral to do. Okay, so, alright, well that's how rectangular worked out. Now let's look at how the spherical thing works out. Here's the various partials. Yeah, there's a bunch of trig in there, that's true. Here's what happens when you take the cross product. Okay, but notice there is a common factor of sine phi in all of the coordinates that I can factor out, and then you'll notice eventually that there's a Pythagorean little thing going on over here, and then after you deal with that handily, you'll find that there's another Pythagorean thing that's going to show up, at least one. I can't remember if it's one or two. But anyway, Pythagorean simplifications, and it turns out that the stretching factor ends up being really nice. Right? So which do you like better? Now that we see how it's turned out, right? These are our two stretching factors, or more to the point, here's the two different integrals that I can choose between for computing the area of this hemisphere. Which of these integrals do you like better? I have a pretty strong preference, right? I think we'll all agree that the one at the bottom's way, way nicer. So I think this is a nice lesson, just in how does this kind of stuff work out in the real world. There's a temptation to say rectangular coordinates is, I'm so accustomed to it, it must be better. No, there's a lot of things about the real world that are intrinsically, naturally spherical. And spherical coordinates are way better for dealing with those kinds of things. Right? Now, we've already seen a couple of examples of this kind of thing, and this is just another example. Hard-fought wisdom from my days as a undergraduate physics major, and of course, like everybody else, I started off, sticking with my rectangular parameterizations and then having to deal with this as my penalty. And you get stung on that enough times, and then you don't want to get stung anymore. So anyway, learn from my pain. Okay. Alrighty. Now here's a nice little special case. We've got an existing formula for our stretching. Oh yeah, question. Go ahead. Yeah.
Previous one.
Yep.
When we switch into spherical coordinates, do we not take into account like rho squared, like the stretching factor?
Oh, that's a great question. Let me talk about that. So that formula that you're thinking about, the rho squared sine phi, that is a volume stretching factor. And if you're looking at how one volume relates to another volume, then that's what you use. Very importantly, that's not what we're doing here. There's no volumes involved, right? So the volume stretching factor just isn't relevant. Now, you may be thinking to yourself, well, yeah, but after all, I was on a sphere where the equation was rho equals 1, and so isn't this actually equal to 1 squared sine phi? Isn't this actually, coincidentally equal to rho squared sine phi? And isn't that kind of the point? And no, it's not. This is an illusion. This is a coincidence. In fact, this little coincidence only comes up in the case of spheres centered at the origin. But it's a nasty little illusion because it's so tempting. Because you look at this and you see rho squared sine phi, and you're like, oh, well, I recognize the expression. That must be the reason. And it's very hard to argue why this won't always work out. But you can just take any surface that's not a sphere centered at the origin and go through this process. Go through this process to find your stretching factor. Anything other than a sphere centered at the origin, and you will not get rho squared sine phi. Yeah. Does that make sense?
Yeah. So when we switch to since we're using surface instead of volume, when we do change the bases, is there no stretching factor related to that?
No, there is a stretching factor. And we've already computed it, right? So the idea, though, is that the stretching factor, when you're talking about surfaces, this is the stretching factor. Yeah. So it's not whether we do or don't. We definitely do. It's just a question of what that stretching factor is. What you don't do is apply a volume stretching factor to an area question. That just doesn't make any sense. But I get the temptation. But that's a square peg round hole. Is that satisfying? Yeah. Everybody else seems okay. All right. Great question, by the way. A lot of students get stuck on that. Cool. Okay, so let's consider the special case of rectangular graphs. And this is a very common scenario to deal with, which is why it's worth thinking through how it plays out. It's just very often the case that you have a rectangular graph. And well, here's the thing. If you have a rectangular graph such as this, right? If you use the graph parameterization, let's see, did I write down the... Well, I didn't write... How about that? Well, here's what the graph parameterization is. I guess this is most of the graph parameterization right here. You just let x equal u and y equal v, and then z is what it has to be. And you can take that, compute the partials. You'll always get these as your partials of x, y, z. With respect to u and v, you can always cross those. You'll always get this for that cross product. And the magnitude will always be this. So it's just kind of a nice how this always works out the same way, at least with a nice little formula. Oh, and I forgot there's a typo in here that I can't fix because this is all done with pencil. Obviously, I just forgot to put in the factor of delta there. Sorry about that. So if you're doing a computation of something, maybe you're computing mass or whatever, who cares, right? When you're doing that computation and you want to pull back through the parameterization, your stretching factor, oh my gosh, my stylus. Stretching factor is always that. So that's a nice little convenience to just remember. And when the scenario comes up that you're dealing with a rectangular graph, which again, pretty darn often, right? Then you don't have to go through and do the whole partials and cross product and magnitude and square roots and simplifying. You don't have to do all that. You can just go straight to, this being your stretching factor. Everybody happy? Okay. All right. That said, two things. First of all, you can't always do this because you can't always rewrite things as a graph. Sometimes it just doesn't work. Sometimes, for example, your surface literally is not a graph. For example, if you have an entire sphere, that is not a rectangular graph. It just isn't, right? Whatever variable you try to solve for, you're all going to have two options, the plus and the minus. So this formula here is not a substitute for the general formula. This is a nice streamlining that is useful sometimes. And secondly, not only does it not always apply, it's also not always better. And let's not lose sight of what we just talked about, right? The comparison here. The rectangular graph would give you that stretching factor and thus this integral. And we've already spent plenty of time focusing on how that is inferior to the spherical option. So don't put all your money in this little bank here. That's a mistake. Okay, moving along. So we're jumping into chapter 15 now. Chapter 15 is to me, the most fun part of the course because there's so many ideas that fit together in so many unexpected ways. It's really very beautiful. The more you learn about it, the better that you understand it, the more you'll see, wow, golly, it really is a pretty beautiful subject. Side effect of this is that there's so many ideas and they fit together in unexpected ways that it is, in fact, pretty challenging, right? So this is arguably the hardest part of the course that we're about to step into, and so, heads up for that. Okay, so anyway, here we go. First thing we need to do is we need to define a new mathematical object, something called a vector field. And I'm going to start by drawing pictures of it. And the big idea of a vector field is that every point in space, we're going to assign a corresponding vector. And when I say I'm going to assign to this purple point, I'm going to assign a vector, what I mean is I'm going to draw the assigned vector in such a way that the tail of the assigned vector is at that point. That's just an artistic option. It's not, whatever. But anyway, that ends up being the natural way to do it. So for every point, there's a corresponding vector. Not just any point, but for every point, there is a corresponding vector. And so you do that everywhere, right? You do, for every point there's a vector, you do that everywhere in the plane, and you'll end up with something that looks kind of like this. Or if you do that in space, right, in three-dimensional space, then you'll end up with something that looks kind of like this. Again, for every point, now this is a point in 3 dimensions, right? You can see, for example, that it's got x, y, and z coordinates. To every point, we associate a vector, and I've drawn a vector arrow there. And again, you can see that's 3-dimensional because x, y, z. Everybody with me? Okay. Importantly, notice that the dimension of the vector you draw has to be the same, of course, as the dimension of the point that you're associating it to. So, 2-dimensional vector when you're in R2, 3-dimensional vector when you're in R3, of course. Yeah?
Are you associating the same vector to every point?
No, that's a great question. No, different points get different vectors. And so, for example, you'll notice, let's see here, this point and that point, you can just see right here they have different associated vectors. That one's kind of pointing sort of northeast, and this one's pointing straight east. So yeah, no, it's different. Every point gets a different vector, or could get, anyway, a different vector. Yeah. Anybody else? All right. We write these as functions, and this is just a way of thinking about it, but whatever point you're talking about, you can think of that point as being the input to a function, and given a point, in other words, there is a resulting, or you might say output, vector that you associate with that point. And so it's literally a function. And so, for example, let's take a look at this one right here. Here's a function representing a vector field, and for every point, x comma y, here's a formula for what we call the field vector, the vector that we associate to that point, and there's a formula for that. And I've plugged in here a specific, at the point 1 comma 2. You plug in 1 comma 2 into that formula, out comes 0 comma 2 as my field vector. And then, of course, that's just one of the field vectors. I mean, if you plug in different points, you get different field vectors. You could, kind of fill up the XY plane with these little arrows and stuff, and get a picture of that vector field. Everybody okay? So, algebraically, this is what a vector field looks like. A vector field is a function where the number of inputs and the number of outputs is the same. Geometrically, we think of it as something kind of like this. Okay. Now, real quick, I do need to point out that these pictures that we're drawing, this is yet another new kind of picture. And remember, I gave you all this multiple speeches back in chapter 13, beginning chapter 13, about how you really got to pay attention to what kind of pictures we're talking about, because if we're looking at a level set of a function, calculus looks very different than if you're looking at a graph of a function, or if you're looking at a parameterization, right? Well, here is and then let's not forget the whole literal picture with the input over here and the output over there. We've seen previously 4 different kinds of pictures that all, in their ways, help me understand what a function kind of looks like, at least in certain senses. We've got 4 of them already, and here's a 5th one. The 5th one is how do we draw a picture of a vector field? And this picture here is not a graph. It is not a level set. This is not a domain target, sort of literal picture. This is not a parameterization. It's just a different kind of picture. So the calculus of, what does calculus look like on these pictures is a whole separate thing that we're going to talk about. And it turns out that the kind of calculus of vector fields we're interested in is, in fact, different calculus. Partial derivatives aren't going to be that interesting on this picture. But there is a different collection of calculus objects that we're going to develop and care about. Okay. Now, just to, get some victories on the board. Here is another vector field. This one's not sort of a freebie, right? I mean, this one up here is sort of a freebie. I got ahead of myself, didn't I? This one's kind of a freebie. You notice all the field vectors. They're all 2, 1. So same vector at every point. In other words, same direction, same magnitude, because they are literally the same field vectors at every point. So that's already a little weird if you think about it. This doesn't look like a constant because you'd think like a constant would have to be like horizontal or something, right? But that's graph talk. We're not looking at a graph. This is what a constant vector field looks like. Okay, here's another example. This one is not as bad as it looks. What's neat about this one is for every point, for example, let's consider that point. Notice that the field vector, in this case, coincidentally, check it out, the formula is the same. The field vector is the same as the input point. Let me say that a little bit differently. The field vector is the same as the position vector for that input point. So there's the position vector for that point. The field vector is the exact same vector. Of course, we always have to draw it. Let's see, I hope this works. I was afraid of that. Oh, man. Let me try that again. I think that'll do it. There we go. The field vector is exactly the same as the position vector. It won't let me. Oh, man. Okay, oh well. I was going to be all cool and high-techy there, but it didn't work out. The field vector is exactly the same as the position vector at the point. Is that cool? All right. So what you get from this, you'll notice, as suggested by this part of the picture, the field vectors always point radially outward with magnitude equal to the distance from the origin, and so you get a picture that looks kind of like this here. All right, so again, a couple of relatively easy ones. This next one is a little trickier. Here, this is not constant. It's not equal to the position vector. What do you do? And we do, however, notice a couple of conveniences about this, namely the point and the field vector have something in common. Have related coordinates. right? And pretty easy observation to make is that the field vector and the position vector, you can see right there in the formulas, they certainly have the same magnitude. Square root of x squared plus y squared in both cases. You can also see that this dot product is 0, meaning that these vectors are orthogonal. So same magnitude as the position vector, but perpendicular to the position vector. And that gives you a picture that looks kind of like this. So again, for any given point, let's say a point there, keep in mind that's the position vector. The field vector has the same length, but is pointing perpendicular. Like so. Anybody on board? And then you can, plug in a bunch of, analogous arguments at a bunch of other points, and you get something like this. Okay. Alrighty. Here's one. We've actually already seen a vector field before. We just didn't realize it. We didn't use the terminology at the time. But let me remind you, we know how to compute gradients, right? And if you have a real valued multivariable function, then you can write down a formula for the gradient, such as, well, for this function, here's a formula for the gradient, and check it out. Sure enough, what we have here is that for every point, x comma y, we get a vector. At every point there's a vector. That's what a vector field is. So now, why didn't we view this as being a vector field at the time? Well, because at the time we were literally looking at just one point. Because after all, I can personally only be at one point on the side of the mountain at any given moment. And if I'm only at one point, then the vector at that one point is all I care about at that particular moment, right? So we just kind of didn't extend the idea because we didn't need to. But nevertheless, we can now, and here's what the gradient field looks like. Right? And just for sort of satisfaction purposes, let me just remind you that the graph of the function looks like this. And you can kind of see here that, looking at the gradient and looking at the graph, and you kind of put them onto the same picture, and notice that this gradient does, in fact, always point uphill everywhere in the domain. Is that cool? Is everybody happy with that? Okay. Now that's just a, observation. Okay, so why are we interested in vector fields? What does this have to do with the real world? Or is this just mathematicians being, abstract? And not at all. There's lots and lots of very important examples of things that happen in the real world that are very naturally modeled with vector fields. And so here's an easy one. The gravitational field, you've probably heard people talk about how, our planet has a gravitational field. It's a vector field. That's why they call it a gravitational field. It's a vector field where the field vector is just gravitational force. Now, there's an easy formula we can write down for gravitational force. You might have seen this in a physics class at some point. If not, here it is. It's gravitational field. And notice, for every point x, there is an associated vector that, of course, the way gravity works is it always points toward the mass that is the source of the gravitational field. So toward the origin in this case. Is that cool? Everybody happy? Okay. By the way, while I'm here, I do want to point out there is something about this formula that kind of throws students for a loop sometimes, and that is students like to think, hey, wait a minute, but I thought gravitational force was supposed to be inverse square. What's with the cube here? And so here's the way to think about that, in my opinion. I would rewrite this formula as negative G M over magnitude of x squared times x over the magnitude of x. And what's nice about this is you will notice that I have not cheated, right? The x cubed, there it is, All three factors are there. But when you write it as I've done here, you'll notice this is a unit vector. So that tells me direction. And the magnitude, of course, is just a scalar that you multiply by the unit vector, and this magnitude, as it should be, is inverse square. So this cube right here is actually kind of an illusion. That's just an after effect of just the way the algebra looks, how the algebra works out. Is everybody okay with that? Okay. All right. Okay. So there's gravitational field is a vector field. If you want to study gravitational fields, which ends up being important for a lot of purposes, you're going to be doing business with vector fields. Likewise, electric fields. And if you've taken an E&M course, or if you're an engineer, you certainly will eventually take an E&M course, then you'll have some familiarity with electric fields, and they are bonkers important. Right? I mean, every piece of electronics. The world has been taken over by electronics in the last, however many years. And electric fields are critical to understanding how those work. So kind of a big deal. And interestingly, you'll notice that they're similar in structure. They, too, are a 1 over the magnitude of x cubed times the position vector x. It's got that same formula, same aspect of the formula as this, right? The only difference is that the constant there is different from the constant there. Slightly different constants because they're different physical phenomena, different physical details, basically, right? But structurally, they look exactly the same. And so now this is a motivation for what I think is a really important point. Even if you do not plan to be an astronaut or to design rocket engines or something like that, even if you plan to be 100% terrestrial in your life and all of your professional career, if you want to understand electric fields, a pretty good way to do it is to understand gravitational fields. And the payoff there is that gravitational fields are more relatable. We have every day walking around unavoidably tremendous experience with gravity, right? Trip and fall, gravity, right? So gravity is super, super relatable and obvious. Electric fields are so subtle and hard to notice, we didn't even know they were there until, a couple hundred years ago. Right? So, certainly, for myself, when I'm trying to understand electric fields, thinking about electric fields, in my mind, it's a teeny tiny little planet that's exerting a gravitational field, except, I know the constants are different. Right? And so, to me, every bit of intuition I have about electric fields and anything related to electric fields comes from my understanding of gravitational fields that I find, again, much more sort of intuitively relatable. All right, moving along. So here's a totally different physical metaphor, you might call it, right? Application of vector fields. There are lots of fluids on planet Earth that flow around in different ways. And of course, you hear fluid and the first thing you think of is water. Sure, fine, right? But air is also a fluid. The pollution inside of air is a fluid. Blah, 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 right? People used to talk about the ozone layer, right? That's a component of the atmosphere, and it is a fluid, right? Not all fluids are three-dimensional. There are kind of two-dimensional fluids, the obvious being how water moves on the surface of the earth. But I like to point out as well that animal migrations can be thought of as a two-dimensional fluid moving across the map. And you may object and say, hey, animals are not fluids, right? But let me just remind you, every fluid, let's take water. What is water made out of? Little particles, right? If you are looking at how water flows, what you're actually looking at is a bunch of discrete things that just happen to kind of move consistently. Well, that's what an animal, you look at a herd of wildebeest walking across wherever they are, they're a bunch of, from a sufficiently high altitude, a bunch of teeny weeny little things that are all moving kind of consistently, right? So it is actually a pretty good model to think of animal migrations as being a flow of a fluid. Okay. For reasons that we will see later, very often the field vector that we use to describe the flow of a fluid is just the velocity. Maybe sometimes we multiply by a constant for units reasons or something like that. And by the way, I don't want to get bogged down in units in this class. That's somebody else's problem. When you take an engineering class or a physics class, they'll worry about that. However they want to do it, their show. The believable reason for why we would want to associate velocity is because if you have a point and you want to describe how a fluid is flowing, well, the velocity is a pretty good way to describe the motion of that fluid. Right? It does turn out, though, that in some cases it actually makes sense for the field vector to be velocity times density, and the reason for that we'll maybe talk about later, but arguably a digression. But anyway, heads up that sometimes it's velocity times density, and I can't later. Okay. Oh, and I see now that I am out of time. So let's see. This is a pretty good place to draw the line right there. Plus, my keyboard battery apparently is low. Picking up subtle hints from my computer there. Okay, see y'all later. Have a good one.